All right, so in this example, we would like to look at the vibrational modes of the nitride ion. So basically N3 minus ion and its theoretical stretches. And they also want to see which of these are IR active, and they want us to stretch this vibrational modes that will give rise to these wave numbers that they've listed there. So the first step is we need to draw this structure. So we have three nitrogens. Meaning N, N, and N. And nitrogen is in group 5. So to count the total number of electrons available here, we need to include, remember that minus there. It is then 3 times 5 valence electrons plus 1 for that. So that gives us 16 electrons that needs to be distributed. Then we need to put the least electronegative atom in the center, and hydrogen always goes outside, but in this case we just have 3 N's, so we just put them in order. Now, we place two electrons between atoms to form a chemical bond. So in other words, from our 16, we just place 2 electrons between each of these atoms. And then we complete an octet on the outside atoms first, and then we go inside. So the outside first, the 1, 2, 3, 4, 5, 6, 7, 8, and 1, 2, 3, 4, 5, 6, 7, 8. So the outside ones are happy. The inside one only has 4 electrons at this stage. Now we can fix that is by donating one of the pairs on either side of the nitrogens. So what we do is, let's say we highlight these ones, and then we basically take them and we move them to here, right? And they're green so that we can remember where they come from. And let's make another group. So we choose these, and then we make a nice little groupy group, which is then going to go there, where they come from. So that forms two bonds. So a double bond and a double bond between our central nitrogen and the outside nitrogen. Now, if you look at these structures and their formal charges, then you will see that there is actually the situation leads to a positive charge, negative charge, and it's negative charge here. So that leads to an overall negative charge like we started with. Okay, so that's how you draw the Lewis structure. And this Lewis structure, there are no lone electrons on the central atom. So in other words, it is linear. So there's nothing that perturbs us from having a deviation from linearity. So this kind of the N3 has a minus, is this kind of linear structure. So to get its number of normal vibrational modes, it means that N vibrational is equal to 3n minus 5. And that is equal to 3 times 3 minus 5. So that is 4 modes. You might also say that this thing is isoelectronic to carbon dioxide, just on a separate note. That is something that you can look up. So you can look up the stretching modes for carbon dioxide and get an idea of what's going on here. Now, the most important part now that we want to do is we want to visualize these stretches to see which ones lead to what. So let's draw nitrogen, 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 and another one. So So we draw 3 options that we can look at, well, actually 4, for all 4 the normal modes. We're drawing structures. I'm going to draw this one below it. Okay, so this first one, let's call it new bar 1. Its stretch will be symmetric, so it will be a symmetric stretch, outward like that, outward like that. And next you should ask the question, so a symmetric stretch like that with it bonded to itself is not going to lead to a dipole moment that is active. So in other words, this dipole moment doesn't lead to a change in dipole, or this bonding mode, vibration mode, does not lead to a change in electric dipole. So this one is not IR active. The next one, V02, they are different options. So what if they all sort of move in the same direction? That's going to give a change in dipole moment. So in other words, this is then IR active. The last one, the only option that, so this is stretching. We've assigned to 2 stretching modes. Now we're only left with bending modes. How can the 2 bending modes look like? Well, we can have one nitrogen enjoy going upwards, and then in the other case, the nitrogens can come in and out of the plane in a different way than keeping the one nitrogen still in the middle. But these that we have here, so these are what we call degenerate. In other words, nu 3 and nu 4 will be equal. All right. The most important thing here, though, is that they are also IR active. Indeed. All right. So now that we've figured out how the stretches look, why they are, and what they're doing, then when we say which ones are the IR active, we can assign the modes. So the one that is assigned at nu 3, so the value of 2041 per centimeter is going to be, it's not going to be that, my apologies. We actually need to keep this rightly formed. So the first stretch is the symmetric stretch, and it should have a wave number equal to 1344 per centimeter. Then the asymmetric stretch, which is nu bar 2, we expect to have the higher energy absorptions. In other words, that's 2041 per centimeter. And then finally, we have nu bar 3, which is also nu bar 4. That is equal to the bend that we saw. So the bending motion, that is 645 per centimeter. Assigned theoretically, because we know V1 or nu bar 1 is not a stretch that leads to the change in dipole, and hence you wouldn't see it in the spectrum because it's non-IR active. Okay, so that's the idea of this question. Thank you for watching.